and thank you very much, Emmanuel, for introducing me and for inviting me to present this work. So the title of the presentation is High Accuracy Thermal Model for Heat Loss Calculation in Power Devices. So let's go through the agenda quickly. First, I'll give you an introduction of the Hexagon Applied Solution group. Then I'll introduce the work that we did. I'll describe the case study that we selected for this specific work. Then I'll go into the details of the model development with the power loss model developed in SIMBA, then the thermal model developed in SIStream, which is an Hexagon tool. And then I'll describe the SIMBA SIStream integration, and then present the results and the conclusions. So Applied Solution Group is essentially an engineering consultancy group within the Hexagon Manufacturing Intelligence division. What we do, I would say, is mainly focused on powertrain design. We cover all aspects of powertrain design, from transmission design, electrical machine design, powertronics, control system, and we also do system integration. Typical project will be designed from clean sheet of paper. So where the customer give us the specification and we do the powertrain design, up to detailed design, prototype and test. But we also do a lot of just focused analysis, optimization, feasibility studies. I would say that at the moment is mainly automotive sector and aerospace, but we do work a lot, especially in the past, in wind turbines, so renewable energies, railway, and marine. So that was a quick introduction of our team. So let's now start talking about the actual work here. So the idea was to basically create this high-fidelity thermal model by starting with the SIMBA model. So we use SIMBA essentially to estimate the power losses on the devices. And then instead of using the 1D thermal model from SIMBA, we replace that with the higher fidelity CFD thermal model, which we have in SIStream. And of course, the advantage is that you can get a much more accurate estimation of the losses in your converter, which then allow you to reduce the margin of uncertainties and potentially saving money in the device choice. So that's the idea. As case study, we chose one of the converters that our team recently developed, which is essentially an onboard charger converter for an automotive. It's still a prototype stage, as you can see. So here you can see a 3D model. On the right, you can see the spec. So it's 11 kilowatt in terms of nominal power. The input voltage on the AC side is 230 volts. We have a configurable output voltage on the DC side. So it can be either 400 or 800 volts to be compatible with most of the cars in the market. It can work both as single phase and three phase, bidirectional power flow, water-cooled cold plate. And in terms of technology, we have silicon carbide MOSFETs. We divided the converter into three stages. We have an AC line filter as input stage. Then we have an AC to DC stage and a DC to DC stage as output stage. Just quickly here, a few more details on the different stages of the converter. So we have an AC line filter where, of course, the main reason is to filter current and voltage so that we don't inject rubbish into the grid. We also have a pre-charged circuit there and protection fuses. Then we have the AC to DC stage with a three-phase full bridge with neutral, and the DC to DC stage, which is a full bridge CLLL topology. Here, just quickly to mention that we finished the prototype assembly. We are currently undergoing experimental validation. So as you can see, we built the experimental setup basically last week. So within the next few weeks, we should also have all the experimental validation, and we should be able to correlate this work with experimental results. Right, so let's move now into the model preparation. So for the SIMBA model, what we did was essentially to focus on the AC to DC state of the onboard charger. The model that we developed essentially is the one that you can see on the screen, and it consists of a power state where we have 3 input inductor filters. Here, the 6 MOSFETs to form the 3-phase H-bridge, and a DC output capacitor here. Then we have a control state with a PLL, which is essentially there to track the grid voltage, and a DC output voltage controller here. Then what we did was to connect the thermal port of the MOSFET to separate temperature sources. And each of these temperature sources will have a different temperature variable, essentially. The reason we did that is because the temperature value inside these temperature sources will be calculated by the CFD thermal software. And I will show you later how we did that. And this essentially enables you to predict the temperature of the individual MOSFETs separately and understand, for example, if your design has got like temperature imbalances between the devices, and so then you can correct it, for example. Just as a comparison, this is how it would look if it was a conventional thermal modeling approach done in SIMBA, where you have all your thermal ports typically connected to the same thermal node. So you basically have same temperatures in all your devices. And then you have your thermal node connected to 1D thermal network, which in our case, we basically have just the thermal interface material, the TIM, and then the cold plate to water thermal resistance, which is probably the most difficult parameter to estimate, because as you will know, it depends on the flow regime, so whether it's laminar, turbulent flow, and it relies on empirical equations. So it's probably the bit where you typically have the largest error. Let's now move to SIMBA. So for who are not familiar with SIMBA, I'll give a quick introduction of what it is. So SIMBA is a package of Cradle, which is our CFD software within the Hexagon MI portfolio. Among the different packages of Cradle, SIMBA is probably the most suitable for electronics thermal simulations, mainly because it's compatible with most of the PCB design exports, such as Gerbil, Drill, IDF5. So you can very quickly import your output from your PCB design tool and set up your model. And you can also model the inside of the of a chip of a device using one of the toolbox there, which is called Electronic Parts Maker. So you can model what's going on inside the device. In this slide, I'm showing the actual SIMBA model of the AC to DC stage of the onboard charger. So we used Altium Designer to design the PCB. So what we did was basically to export Gerbil, Drill, and IDF files and import them in SIMBA. So it took us just a matter of minutes to set up this model. Then within SIMBA, we modeled the internals of the MOSFET. And this basically includes the mold, which is essentially the plastic here that encapsulates what's inside the MOSFET. The plate, which is the green area here, which is essentially the metal part that is used to extract the heat from the inside of the MOSFET. The leads, which are the connections to the PCB. The chip area, which is where you apply the losses. So losses are applied on the dark gray area here. And then we also have the bonding between the chip area and the plate. And then we also included the model of the thermal interface material that we used. We also did the model of the water-cooled cold plate, which is essentially an aluminum plate with a copper pipe with 4 passes. In terms of boundary conditions, we have a flow rate of 5 liters per minute and an inlet temperature for the water of 60 degrees C. Right, and then so now we have the 2 models. Then the next step was to for this proof of concept was to develop a Python script. So we chose Python to develop this interface between SIMBA and SIMBA. So the way this script works is that essentially we run SIMBA to get the losses, the power losses on the 6 MOSFETs, which are then saved, stored in a TXT file, which is then used as input for the SIStream thermal simulation. So SIStream calculates the temperatures then on the 6 devices, writes them on another TXT file, which is then read back into is feedback into SIMBA. So this process goes on till we reach convergence, and the temperature reaches the steady state. So we are solving a steady state thermal simulation here. And in a standard engineering laptop like mine, it took about 2 hours to solve this with around 1 hour and 54 minutes. Right, so in terms of results, so what I did is to essentially first run the standalone SIMBA model, which is just SIMBA with the native 1D thermal network in SIMBA, and get the power losses and junction temperature. Then these loss values can then, the next step will be then to input these loss values into SIStream to improve your thermal prediction. However, this doesn't do the feedback loop, doesn't close the loop. So we don't capture essentially the variation on the power losses, on the temperature dependent power losses of the MOSFET. So the next step is what we propose is to actually close the loop and essentially let SIMBA get the most updated temperature to improve the power loss prediction as well. And one final slide on the results, just to show how you can also visualize the results then from the post-processor of SIStream, where you can isolate different components, for example, the MOSFET or the chip area inside the MOSFET to see if you have hotspots or the cooling water. Before concluding, I just wanted to add a couple of slides of a new capability that we are introducing, that the SIStream team is introducing. This will be released at the end of November, so it's not there yet, which is the boundary condition independent reduced order model. It essentially allows you to start from a full order model, reduce it, so get a much smaller model to essentially solve your thermal simulation much faster. So this will allow you to, for example, run transient thermal simulations as opposed to just steady state simulations. So we did that, for example, we tested this on a transient thermal simulation with a time step of 0.1 milliseconds and from 0 to 30 seconds. So you have to set the boundary conditions and the heat source. So for the heat source, we took the transient data simulated in SIMBA. And these are the results. So basically what we have is that it took almost 7 hours, which is quite a bit of time to get this reduced order model. The main reason is that the full order model was very, very large. It was 11.5 million elements, because we basically modeled also the traces, the copper traces inside the PCB. So it was very, very detailed. And the reduced order models was 4,200 elements. For the simulation time, it took the full order model 321 hours on a 4-core machine, and for the reduced order model 2 hours 17 minutes. So we have a speed up ratio of 140 times, which can be increased even more if you choose even smaller reduced order model. And of course, the accuracy that we get is very, very good. Right, so this is my last slide. So for the conclusions, just wanted to summarize what we did. So we achieved this integration between SIMBA and SIStream, which allows, of course, to predict accurately losses and temperature. Of course, by doing this, you improve your confidence in your thermal behavior of the converter and will allow you potential saving on the selection of devices. You can use the 3D temperature map visualization in SIStream to not just know the average temperature of your converter, but you can also understand where you have hotspots and improve your design. And finally, with the BCI-ROM capability, you can even run much faster your simulation and do transient thermal simulations. And finally, I just wanted to add that as a consultancy group, essentially, the way we typically deal with this project is essentially either offer them as one-off engineering service, or recently we essentially developed a new tool called Nexus, which is essentially a cloud-based platform where you can interlink different softwares, not just within Hexagon, but also with third-party software. So we can, for example, connect via Nexus, SIStream and SIMBA to automate the whole process. And that's all from my side. So yeah, feel free to ask me question, and here is my email address if you want to contact me with further question or clarifications.